Okay, we're back for our last two sets of problems. Number one, you have a 1.5 kilogram cart that you place on top of a ramp that starts 0.6 meters above the ground. How much potential energy does the cart have on top of this ramp? Well, this is easy. This is just asking us how much potential energy the cart has. We know how high above the ground it is, and we know its mass, so we should be able to do this very quick. PEG equals mgh. The gravitational potential energy is equal to 1.5 kilograms multiplied by 9.81 meters per second squared, multiplied by the height of 0.6 meters above the ground. 1.5 times 9.81 times 0.6 gives us a potential energy of 8.829 joules. Here we go. Okay? Now, B says, assuming no friction, when the car gets to the bottom of the ramp, how much kinetic energy does it have and how fast is it moving? So this is a case where, okay, now we probably do need to use conservation of energy because we have something happening. We have an event taking place. It's a pretty simple event, and if you remember from the beginning of this work unit, work and energy, we had a problem where we figured out how fast something was moving at the bottom of, let's say, a ramp. We had something, and we'll talk about that more in a little bit. This moves 0.6 meters. Let's see, once again, do the applied force, tension, or the normal force do any work? No, no, and no. No one is pushing this. There is no ropes involved, and the normal force, once again, is perpendicular to the displacement at any point in time. So we know that no work is done, and we know that the initial is up here, and the final is down here, so we can say that ET equals ET. Up here, no kinetic energy because it's not moving, there are no springs, and it hasn't moved yet at all for any internal energy to be generated. And it says assuming no friction, so no Q. The only thing it has is gravitational potential energy, PEGI. Down here, no more gravitational potential energy because it's made it to the ground. No springs, no internal energy because no friction, but we know it's moving fast, and it even says how fast is it moving, implying that there's kinetic energy, KEF. Now I'm going to do something, okay, so first it says how much kinetic energy does it have? Well, wait a sec, we just found how much gravitational potential energy it has up here. So this first question is very easy. 8.829 joules is the initial gravitational potential energy, and based on the equation we just wrote, that's got to be equal to the kinetic energy at the ground. Okay. How fast is it moving? Once again, that's pretty easy to find. KEF equals 1/2 mVF squared. That's 8.829 joules equals 1/2. The mass is 1.5 kilograms, and we're looking for VF. So 8.829 divided by 1/2 divided by 1.5, and we're going to take the square root of that. Oh, I'm sorry, I messed that up. Divided by 0.5 divided by 1.5. There we go. Then we take the square root of that. We end up with a final velocity of 3.43 meters per second. Now, let's think about this one before we actually try it. If, during the cart's descent, its internal energy increases by 5 joules, what would its final speed be? So what we're saying now is there is some internal energy generated. And if internal energy was generated, the only way that happens is through friction. So if friction is acting on this cart, what do you think happens to it? Okay, well, if friction acts on this cart, then what that means is it's not going to be moving as fast. The acceleration down the ramp is not going to be as big. Actually, to backtrack to here, remember when we did this at the very beginning of the work unit, we said you have to have a free body diagram, you have to write net force equations, you have to do kinematics equations. Those are like 3 different things to do. Look what we did. We did essentially one thing. We used energy conservation. We got a final answer very quickly. So in some cases, energy is actually, when you can use either kinematics and forces or energy ends up being quicker to use. Not in all cases, but in some, like this one. Anyways, back to what I was saying. If there's now internal energy for this cart, What that means is that friction must be acting on the cart as it goes to the ground. And if friction's acting on it, friction opposes motion, it reduces the acceleration. We should expect the final velocity not to be as high. However, we can still say that energy is conserved because we're now going to account for the internal energy. We can still say, because we know the internal energy should decrease the kinetic energy. We still start with ET equals ET. At the top, it's still just got gravitational potential energy initially. It doesn't have internal energy yet because it hasn't done any moving yet. Friction hasn't done any work. There's displacement is 0. As it slides down, when it gets down here, now it's generated some internal energy, so we can write Q, and we're going to assume, because it says what's its final speed, that there is also some kinetic energy that's generated, okay? We already know, let's see, and we could actually solve it right here. We already know how much gravitational, actually here, let's hold off for just 1 second. The only reason I'm doing this is because we want to have the equation for kinetic energy written out. 1/2 mv naught, or v final squared. We already know how much gravitational potential energy there was. That hasn't changed. The internal energy is 5 joules. And if you think about it, if this is 5 and this whole thing has to be equal to 8.829, the kinetic energy has to be whatever the difference is between these two. And if it's the difference, then it can't be the 8.829 that it was before. Kinetic energy must be less. After you solve for VF, you should find that the final speed after it slides down, with friction this time, is only 2.26 meters per second. Now, we know that that happens because friction takes away, friction causes the acceleration to not be as high, so it takes away some, friction causes the acceleration not be as high, so it can accelerate to as high of a speed. Now we also know that this is because internal energy, as the gravitational potential energy decreases as we go down, both the internal energy and kinetic energy are increasing as it goes up. And because there's only a limited amount of gravitational potential energy, now not all of that is getting transferred to kinetic energy. Some of it is internal, so the kinetic energy must be less. Therefore, the speed must be less. I got one more example for you. An 87 kilogram skier at the top of a hill that is 30 meters tall skis down to the bottom. At the bottom, his speed is 16 meters per second. How much mechanical energy has been lost due to friction? What we're essentially looking for here, energy lost due to friction means find Q. Okay, it hasn't really been lost, it's just been transferred into internal energy. So we've got a skier at the top of a hill. Hill's 30 meters tall. Here's our skier. Okay. Once again, no applied force, no tension, and the normal force is always going to be perpendicular to the direction that the skier is moving in. The only time where it's not, you've seen times where it's not, think about like an elevator. Normal force is either parallel to or anti-parallel to the direction of motion. But if you've got something like this, that normal force is always perpendicular to the direction that the skier is moving in. Okay? So no work is done. Here's initial, here's final. We have ET equals ET. All right? So up here, we have gravitational potential energy in the initial spot. Down here, we know he has speed at the bottom, so he's got some final velocity. I guess I should have said the skier's at rest, but I mean, we usually just kind of assume that unless it says otherwise. He's got some final kinetic energy. And if we're looking for how much energy, mechanical energy, has been lost due to friction, that means we're finding Q. Let me show you how another check for how you know that that's what you're finding. We know gravitational potential energy is mgh initial equals 1/2 mvf squared plus Q. Now let's substitute in for these. We can't cancel out m because Q does not have an m term in it, and we're just looking for Q. So this would end up being, let's see, 87 kilograms, 9.81 meters per second squared. The initial height is 30 meters, 1/2, 87 kilograms, 16 meters per second squared plus Q. If I do the math on these, 87 times 9.81 times 30. I end up with a initial potential energy, just multiplying these out, MGH, of 25,604.1 joules. If, on the other hand, I find the kinetic energy at the end of the run, look at that. It's only 11,036 joules. So very clearly, if I didn't include internal energy here, you would be stuck saying, wait a second, that's not equal to that. If I didn't include Q, you'd be like, these two things aren't equal. Energy was not conserved. By realizing that some energy turned into internal energy, we are allowing conservation of energy to play itself out. The internal energy is what we haven't accounted for yet. So, to solve for Q, we simply subtract one from the other, so 25,604.1 minus 11,136. We end up with a Q of 14,468.1 joules. Now, if I really wanted to, I could go and find, well, actually, no, because the slope, never mind, I don't want to say that. Because the slope is different, I think it would be a little difficult to find the coefficient based on that. But we do know how much energy was lost due to internal energy, or was turned into internal energy, and this energy is simply something, what was it going for? This energy is simply turned into heat energy, okay? The skis and the snow around them, to an extent, warm up a little bit, okay? So we have seen, once again, how to use conservation of energy. Your homework for tonight would be to work on the work and conservation of energy multiple choice packet, or the questions in the packet. I think there's 25 of them. Some of them are conservation of energy questions. Some of them are work equals change in ET questions. It's up to you to determine what the difference between the two is. Because this is a multiple choice and I'm not right in front of you grading this, I am going to ask that you at the very least show the work on these questions, even if it's just real quick jotting down the numbers. I can't really accept any of the questions where you're just circling something. Even if it's not a mathematical question, give me a little bit of explanation. I need something along those lines, okay? So I'm not going to be super strict about, like, you have to have an equation, you have to have units, but you need to show me that you actually did the work of thinking about this, okay? No just circling answers. I will not accept that for homework. If you have any questions, this is a tricky unit, okay? There are some tricky questions. This is probably the most advanced math that we're going to do. I think there's really 3 topics that are fairly advanced in math. I think it's this, projectile motion, and some of the more complicated, like forces on a ramp questions. That's as hard as the math gets, okay? We'll see some questions that are along these lines, maybe even a couple more terms. But this is, again, like I said, pretty much as hard as the math is going to get, and it's pretty much just algebra. If you have any questions, please ask me. Please get at me on the Remind or anything else. Make sure that you are, if you can, stay in relatively healthy. Try and find some stuff to do. Read books. Watch, TV programs. Don't spend your whole time watching TV. Get some exercise if you can. If you need anything at all, let me know. And I look forward to seeing your work. All right? Have a nice day.